you. So again, our first speaker, Jack Kuta, is a master's student from University of Michigan. He's going to talk to us today about time-encoded dual particle imager. Jack, the floor is yours.
Okay, thanks, Sean. So yeah, I'm going to be focusing on a handheld cylindrical time-encoded imaging system desirable for nuclear non-proliferation efforts. So pretty much what we'd like to have is a simple, man-portable system. And the issue is when we go from a large system to a small system, we're actually decreasing the diameter of our mask. And in doing so, that's really decreasing our angular resolution. So if you're unfamiliar with the cylindrical time-encoded imaging, so here's our detector right in the middle, and this will be our mask here, which I've shown as a fully closed mask minus one little open element here. So if you have a source, right here where this arrow is, pointing towards this system right here, and this mask will rotate around, and it's going to see a time modulation of counts. Only seeing a spike in counts when it's in front of this open element here. So we're moving to a smaller system, which will essentially have a smaller diameter of this thin mask. And so since we're losing this this angular resolution by going smaller, we have to kind of come up with ways to increase our angular resolution and improve our image quality. So what we do is we increase the thickness of the mask. So that'll give us better collimation. And essentially we're going to have several different designs to kind of improve neutron image quality, gamma ray image quality, and then look at different patterns, stuff to improve our overall image quality and actually optimize this handheld system. So our first design is going to be more focused on neutron image quality. So if you can see here, these two designs, this is not to scale, but this will be a larger system, a larger diameter. So here we just have our detector. We have a thin tungsten layer mask and a large polycarbonate mask, which is what we're using for because we're doing 3D printing instead of polyethylene, but it's very similar. So these will be neutrons here coming in, and the green is detected. So this is kind of a standard model for cylindrical time-encoded imaging, which you actually see in Neural's presentation next. However, since we're going very small, a small diameter, we essentially want to keep the mass the same of this mask, and we're just going to decrease the infill of this polycarbonate. So we'll, instead of having it be a very compact polycarbonate, we'll instead have like a tetrahedral structure. So there'll be a bunch of air in here, and we'll just increase our outer diameter of our mask, and we'll keep it at the same mass. So hopefully that should actually improve our collimation, but again, it might increase or decrease the attenuation through the mask, since it's going to be there's less of an infill. So there's going to be hopefully some neutron image quality improvement here by increasing this density, by decreasing the density and increasing this outer diameter. So our next two designs are going to be focusing on gamma rays. So again, these two would be the same size, not different sizes as in the previous slide. And we're going to be adding this tungsten layer on the outside. And this can be the same thickness, or it could be thinner than this one here. And that'll be obviously increase our mass a lot if it's the same thickness as here. But we're going to be having a system that can account for all this. It can actually use these thicker ones or thinner if need be. So we're having this outer layer so we can essentially decrease the admittance through this mask, through these closed elements. These are now gammas. We're not looking at neutrons. So this tungsten hopefully will block or attenuate these gammas. So next we're going to be looking at something a little different. We're not going to have the tungsten on the outside, but instead we're going to have these thin tungsten walls on the inside of every single open element on the sides. And this will, change the scatter essentially, with a Compton scattering angle of, like 30 to 45 degrees, which is, the average. This could, scatter away from the open detector elements or into, a different sidewall. So either way, we're hoping that it's going to decrease kind of the escape of these gamma rays, outside of our closed mask elements. So that should overall, improve our, image quality by decreasing what's going through the closed mask elements. And so next, we're going to be looking at our detector setup, which overall, we're just going to be using a 2-inch steel beam crystal coupled to an SIPM with a summing board and a power board, both supplied by Sandia National Labs. So this entire system will be flipped upside down and put in here. We're going to have our crystal being able to sit right in here. And this is a 3D printed, like a 3-piece set. So this piece will hold the crystal. This is just the housing. And this piece will just be for the wires to go through. And it'll be nice because we'll have these, different pieces that we can kind of switch out crystal very easily. But for now, we're just going to be focusing on a still beam. So next we're going to be looking at kind of the system of itself. So we have this light type box again here. This is the top piece where the crystal is going to be held, so flipped upside down from what we just previously saw. And a big thing here is that we have this mask bed, and it's got a bunch of different slits, 42 overall. So we can have this, and we could have a 42 element mask, which is good for a mask anti-mask system, which is good for several imaging applications. However, we can then cut this up, or we could pair all of these polycarbonate mask elements. And if we wanted to pair them up in two, we could have essentially a 21 mask, which has a Eura. The issue is the 42 element mask does not have a Eura, which is a uniformly redundant array, which is great for ideal coded aperture. And since we don't have a Eura pattern, we can have all these other combinations of mask elements by just pairing it up, and we can have this 21 element mask. There's two different patterns for a 7 element mask, 6 and a 3, and also a 2 and a 1 and a 0, but those will never be used. And we're going to be using here, so we see our 42 element mask would be right about here. And we see there is a Eura for 40 and 43 element mask, and we'll be using those for validation when we're actually making a mask pattern for our 42 element mask. So that's very important that we'll talk about later. But then here we can kind of see the construction of it. So this rotary table will be underneath, and it'll actually be holding the light type box, and there'll be a piece going through the rotary table that'll actually keep the light type box rigid and not rotating, while we then have the rest of the mask bed here rotating around it. So since we don't have a Eura pattern for the 42 element mask, an ideal coded aperture, you're looking at just this element right here. So you're just looking at the periodic autocorrelation of the mask pattern, A cross A. And if it's a Eura pattern, you're going to get a delta function. And that's great for ideal coded aperture, because then you're having a delta function, the periodic cross correlation with this detector response autocorrelation. However, since we don't have a Eura pattern for this 42 element mask, we want to rearrange this point spread function so we actually look at the detector response. So here, this is what we originally had, ideal coded aperture just here. So we're looking at, this guy. We're looking at, A cross D instead. So we're just essentially producing a ton of, random mask patterns for this 42 element mask. And as long as we make all of these, we can try to, find one that has, this A cross D close to a delta function. And if we can do that, then this delta function, if we close to a delta function, cross with another delta function, will give us a delta function, which will definitely overall increase our image quality. However, we know that we're probably not going to actually get close to this. We're not going to get our full like close to a delta function, but we're going to try to. However, this is also only really super useful for like the thin mask detector design, which we saw at the beginning. Because for the thick mask design, the second you increase the thickness of your mask, you're actually introducing a couple other terms into this point spread function that kind of changes the actual overall equation, but still very useful for designs that actually have a thin mask design. And then we'll be using the 40 element Eura and pattern and the 43 element Eura pattern to kind of validate our process of actually picking a good optimized mask pattern for our 42 element. So overall, this is very good for non-proliferation efforts, especially in source verification and search operations once the system's actually built. And it's also great because having a compact, cost-effective fast neutron imager is very desirable. And if this is successful, then we'll be able to test several unconventional encoded mask designs, including ones beyond just the 3 I mentioned. Also hopefully coming into different neutron optimizations instead of just the single variable density mask. And also we can hopefully increase the technological readiness level of this, so we can actually have a physical handheld system that can be used instead of just one that's just placed on a table to test different designs like we currently have. And so hopefully I'll be interning at Sandia National Labs once this pandemic is over, and I'll be looking at different cylindrical time encoded imaging designs, using my system and also using other systems to better understand how I can look at these different unconventional designs. And this is all in collaboration with the Radiation and Nuclear Detector Systems group at Sandia National Labs. And so overall, we have we're losing this angular resolution, so we need to gain it back. So we're having these unconventional mask designs at the variable density for neutron collimation and attenuation, And then we have the 2 for the gamma ray collimation. The closed element attenuation, really decreasing that admittance through the mask, and then the decreased, escape through the mask, which is what the hollow mask was for. And then we want to have our test bed so we can actually test all of these designs and new designs coming up as well. And then we want to be able to have our mask pattern optimization since we're using 42 elements as our maximum number of elements for our mask. We want to be able to make sure that we actually have a good pattern for that, and that we don't have to just pair them all up and use the 21 Eura, although that could still be very useful. And so hopefully, we can construct this very soon. We actually have, parts that are being 3D printed right now. So hopefully we can actually really get this system built and start doing some testing soon. And I also like to make some new unconventional mask designs for neutrons beyond just the variable density mask. And also possibly doing multiple detection crystals, which we're gonna have, which would be like one crystal on top of the other, which for increased like gamma resolution or whatnot, which you actually see in Neural's design in the next presentation. And also possibly make a 2D mask design, since all of these designs are just 1D currently. We might do that with Sandia National Labs, but that work is yet to be set. And I'd really like to thank Sandia National Laboratories and Melinda Sweeney for her technology that she shared with us and all the group's valuable research and technology. And I'd also like to thank our NNSA and DOE sponsors for their continued support of all of our research and this project.
Great, thanks, Jack. Nice presentation. We have a few questions in the chat, so I'll start with those. The first question asks about the materials. So you mentioned a tungsten layer and a polycarbonate layer.
Yep.
And the question is asking about the purpose of the tungsten layer if you're primarily concerned about neutron imaging. So can you speak more about those material choices?
Yes. So, I mean, although the point of the project is mostly, originally to look at neutron collimation or like neutron image quality, we'd also like to still focus on the fact that it's a dual particle system and still focus on those gammas as well. So having the tungsten is very important for the gammas. And those 2 designs, the second and the third, where we're increasing the gamma collimation, that's still very important because, I mean, there's always going to be gammas where there's neutrons. So we really want to, be able to tackle both of those issues, despite, it primarily being focused on as a neutron imager.
Mm-hmm. Question just came in. It's a follow-up to that one. Is why polycarbonate and maybe not something with a different HC ratio?
So I did some attenuation calculations, and what we've historically used is just polyethylene. But with the company we work with for 3D printing, they have a really good process for polycarbonate. And it's a very easy one to 3D print. And if we were just looking at like high density polyethylene, we want to keep something close to that. Polycarbonate was working really well for that, and it was just very easy to 3D print.
Mm-hmm. What's the performance degradation compared to polyethylene?
Ooh.
Roughly. I mean, it's worse, right? But okay.
Yeah.
Okay, good. So it's a bunch of questions in the chat. This is great. I can't even follow them all. Make the window bigger. What if there are 2 sources? How does the system perform if there's multiple sources in the field of view?
So you'll probably see some of this in Neural's talk. So I mean, it's essentially you're going to see several bumps in your image, your overall reconstructed image. And I guess we're going to see worse angular resolution between the 2, but hopefully you can still by increasing the different collimation and having those different like tungsten sidewalls, if we're just looking at just thinking of just gammas, hopefully by having those extra layers of collimation on the sides or at the outer edge, we're able to kind of distinguish those sources better by if one is in front of a closed element and one is in front of an open, we can really focus on just that one by increasing the collimation through the increasing the attenuation and decreasing admittance through those closed mask elements. So I guess it's the same as standard cylindrical time encoded imaging, but we're just trying to recover some of that angular resolution, especially if there are 2 sources.
Yeah. So you talked a lot about the Eura and the desire for this delta function type response. So this most recent question is asking about why is delta function desirable? Can you expound upon its connection to the Eura and why this pattern is needed for 1D identification?
So yeah, so a Eura pattern essentially when it's convolved with itself, you're getting a delta function. That's very important for when you're creating your point spread function, you just have your mask pattern convolved with itself, and that's convolved with your detector response convolved with itself. And if you have a Eura, then you're almost completely disregarding that first term, that A cross A, saying you're only your image reconstruction, in your point spread function, you're only really focusing on just your delta, your detector response. So that's just going to be giving you some a cleaner image if you can have a delta on one of those sides or on both sides. So you'll just have less bumps, and your essentially your full width half max of your in your image is going to be much better if you have a cleaner point spread function.
Good. We'll shift to the hardware side now, about the SciPM readout and the summing board. So the question is, how many pixels are you reading out? Are you using to read out the still beam? And can you speak more about the summing board? Was that Michigan developed or Sandia developed?
That's Sandia developed, and I haven't done any testing. I don't remember the pixel count on there. Might be 16 by 16. I don't
Yeah.
remember. I'd
How
have
big
to
is
look into that.
the still beam again?
It's a 2 inch, so
Okay.
it's a 2 by 2 or 2 inch.
Yeah.
Still SIPM as well.
Yeah, and you just plop that onto the middle of the array and however many pixels it covers.
Yeah.
Yeah, that makes sense. Also on the hardware side, question about how mobile the system will be at the end. And I had a similar, kind of a related question, which is where did the data go? You didn't really talk about, is that all going to be in this handheld form factor as well? Like, how do you plan to deal with the data in terms of mobility?
Yeah, so for right now, we're very, beginning of this level. Our technological readiness level is not, a full handheld system that we can pick up and move. Like it'll be completely, the readout and everything will be completely separate. We'll just have like wires going from underneath. So for right now, if we're doing any testing with this, it's going to be on a cart, and it's going to be at one end of the cart, and all the electronics will probably be, next to it. It's not, ready for handheld use. So right now, it's all just, testing. And then hopefully eventually we can increase our technological readiness level, and we can be able to actually have it all compacted in there, have an actual top we can actually physically pick it up, but currently it's just open to the air on top. So I mean, it's not a full compact design yet.
Mhm. Great. Another question about multiple sources. So if you have two sources in the field of view and one is significantly stronger than the other, have you looked into those effects?
No, and you'll actually be hearing some of that in Neurals.
Okay, good.
Neurals talk right after.
Okay, I think that covers all the questions in the chat. So thanks everyone for those great questions. We have maybe another minute or two if anyone has a question they want to ask. Feel free to just unmute yourself and go ahead.
Hi, John. This is On Hee. What is the effect if the background is not uniform, in terms of angular distribution?
So, I don't know. I guess it really depends. Because with a smaller system, we're not going to be able to block some of the excess scattering, especially background from above or below the system. We're only really able to really distinguish between our field of view, and then that's why we made it kind of wedged here. So essentially along this line this way and this way this is our only field of view that we can actually really say anything good about. But there could definitely be a non-uniform background coming from below or the sides, or really on any side of this era, and accounting for that background is definitely difficult, and not something I've looked into. So I think I have not looked into that.
Yeah.
Okay, thanks, Jack. Nice job again. And if you'll let go of your screen, we'll move on to the next speaker.
Thanks.